So today we're going to be going over the Henderson-Hasselbalch equation and relating this to buffer solutions. Now why do we have the Henderson-Hasselbalch equation? Now this equation was actually derived by a guy named Henderson, and Hasselbalch, Swedish scientist, actually took what he found and wrote it in terms of logs. So that's why they sort of have this compound name, Henderson-Hasselbalch. Now, why do we actually use this equation? Why is it useful? It allows us to approximate the pH of a buffer solution. Now, what actually is a buffer solution? A buffer solution is a solution that we use to resist changes in pH. And now, where is this useful? This is useful in things like skincare products we use, detergents, cleaning agents, or a tool to help us calibrate something that measures pH, like a pH probe. We use a buffer solution because its pH doesn't really change, and so it's reliable. And say if we were to use it in a soap, we would want a buffer within it that would match the pH of, say, human skin, approximately pH 5.5, slightly acidic. And that would be good because it wouldn't harm us when we use it. Now, what actually is a buffer solution? A buffer solution is a solution that contains within it, as its components, a weak acid and its conjugate salt. Now, why do we say weak acid and not strong acid or moderately strong acid? It's going to be explained later. Now, this is especially important because without these two components, it wouldn't be classified as a buffer solution and wouldn't be able to resist changes in pH. Now, let's take an example of a buffer solution and see how we can sort of derive what it has within it and how it uses that to resist changes in pH. So we have a weak acid. Now, how do we denote any arbitrary weak acid? We call an acid HA. Now, why do we call an acid HA? Well, A is just a letter. We take the first letter of the alphabet, say, because it's so arbitrary, and we have H. And H would be our hydroxide, our hydrogen ion. And now, this is important because we know the acidity is defined by the concentration of H plus ions within a solution, and that's why pH is the negative log of the concentration of H plus ions. Due to the nature of this negative logarithm, the more H plus ions you have, the lower pH will be, and the more acidic your solution will be. So that's why we call HA our acid. So say if we took HA and dissolved it in water, so an aqueous solution, this would normally dissociate to form an H plus ion and its conjugate base, which we know from this equation will be A minus. Now, how can we tell something is its conjugate base? Now, we can tell that by it being something, a chemical, that would lack an H plus ion that would otherwise render it into said acid, that acid being its conjugate acid. So we took A minus and added an H plus. Just doing this reaction, looking at this reaction in reverse, we would get HA, which would be our starting acid, our conjugate acid. And just to start us off, one of the reasons why, as a hint, we need a weak acid, because we know weak acids, unlike strong acids, do not fully dissociate in aqueous solutions. They actually only partially dissociate, actually very weakly dissociate, barely dissociate at all. So this would in fact be a reversible reaction. Now, why do we need a conjugate salt? What do we say when we say conjugate salt? It means that it's a salt of its conjugate base or conjugate acid. So if our acid chosen was HA, our conjugate salt would be, it would have to include A and any other metal that would render it a salt. So let's say sodium, it would be NaH. The in solution would actually completely dissociate into sodium, which would act as a spectator within this reaction, and A minus once more giving us our conjugate base. Now, how is this useful? So, we say it resists changes in pH, so that would have to mean that it resists an input of a different substance of a different pH. So let's say our buffer solution was trying to resist addition of an alkali, so adding an alkali. So let's make up a buffer, shall we? Let's do an acetic acid buffer. Acetic acid, also known as ethanoic acid, is given in formula CH3 COOH. Now this is our weak acid chosen. It's quite a high pH for an acid. It's quite weak, so we know it only partially dissociates. And let's take our conjugate salt of sodium acetate. It contains an acetate ion within it. So this is given by CH3 COO, and instead of H, that would give it its acidity as sodium. So within an aqueous solution, so we're adding distilled water or equivalent, our acetic acid would partially dissociate, so we know this is a reversible reaction, into an acetate ion and hydrogen cation. This is what gives it acidity. Now, let's take our sodium acetate, CH3, COO, and A. This would completely dissociate into our acetate ion and sodium. Sodium here acting only as a spectator cation. So let's choose an alkali to add to this buffer solution. Let's take sodium hydroxide. Quite a strong, actually a really strong alkali. pH of approximately 13. Now this is NaOH, and we know that NaOH in the same aqueous solution that our buffer would be in will completely dissociate into Na, sodium, once more acting as a spectator cation, and OH, anions, hydroxide anions. Now, this is really important because this is what defines alkalinity. We know that H plus defines acidity, as given here. We know that OH minus defines alkalinity. These actually come together to form water, H plus and OH minus, which results in neutrality. We know water has a pH of 7, rendering it neutral. Now, how does it resist changes when an alkali is added? So we know that the thing that determines alkalinity will be this OH anion, and we know that we've added acetic acid. What acetic acid actually does when OH anions are added into solution is it reacts with them. So we have CH3 COOH plus OH minus. This hydrogen will actually come off and join there. So we now have an acetate ion and water. So now what we've effectively done is we've converted what otherwise would be a very alkaline solution, very basic, into something neutral. This resists the changes of pH. And the second way this actually happens is we know that when we first inputted acetic acid, we know that these are spectators, so we can just ignore these. These aren't important. But we know that when we inputted acetic acid, other than partially dissociating, very weakly dissociating into acetate ions, we also created a source of acidity, H plus hydrogen ions. These hydrogen ions, as previously mentioned, can also come together and combine with the hydroxide ions to form water. Basically, this whole thing revolves around losing hydrogen and allowing it to form with the hydroxide ion and converting it into neutral water, pH 7. Not going to have a large effect, no effect, little to none effect on the pH of the actual buffer solution, meaning that the effects that sodium hydroxide would otherwise have on a buffer, it no longer has. I forgot to mention, this reaction actually here is actually slightly reversible, because this, so it's sort of tiny backwards arrow, this acetate ion can actually combine with hydrogen ions from the self-ionization, the self-dissociation of water. Water very weakly dissociates, it varies with temperature, but water does dissociate naturally in the reversible reaction to form hydrogen ions and hydroxide ions. Now these hydrogen ions actually once again react with these acetate ions to reform acetic acid, replenishing its supply and allowing this reaction to go on farther, increasing what we call the buffer capacity of the buffer solution. Its buffer capacity being the amount it can resist, the amount of alkali it can resist. It's actually given as how much alkali is needed to alter the pH of the buffer solution typically by 0.1, because that's when the buffer solution is going to break. It's going to reach its limit and it's not going to be able to resist changes in pH anymore. And so this H plus ion is actually going to combine with this acetate ion, as we can actually see in this first equation, and go backwards and replenish our supply of acetic acid. So instead of what would usually be, say this is pH and this is volume of our alkali added, instead of pH starting off with wherever our buffer solution would be and increasing sort of in a linear fashion until the effects of pH of our initial buffer solution are completely negated and now completely match the pH of the alkali. So say this is the pH of the alkali. It will now actually maintain it for a lot longer until its effects are finally broken, where it suddenly springs up and reaches that same pH point. So this reduces all of this that we would otherwise lose. So now let's go on to something else. Let's say we're not adding an alkali. Say we take the same buffer solution, but we're adding an acid. Now, the reason that this is so important is because, the reason that adding a conjugate salt other than a weak acid is so important within a buffer solution is because it allows acid, a source of acid, to be heavily resisted within it. So our conjugate salt was sodium acetate. Now, this we saw dissociated CH3, COO, and A. It dissociates under aqueous solutions into our acetate ion and our spectator sodium cation. So this we can just negate. This is not important. What's important here is this aqueous acetate ion, which is going to react with our source of acid. So we took any given source of acid, HA. The thing that's going to play a part here when it ionizes in water is this H plus ion. This is what defines acidity. A minus we don't really care about. This H plus ion can react with this acetate ion given through our conjugate salt. So we say CH3, COO minus, plus H plus, our source of acidity, and I'm sure you can see where this is going. It's going to change this into acetic acid. But you may say, this is an acid. Why does it not do the same thing? We're just reducing an acid and we're creating an acid at the same time. Well, this is just a pure acid. This is the strongest form that an acid can take. It's a pure hydroxide ion. We're instead converting this into acetic acid. While it does create an acid, its level of acidity much closer to our starting pH of our buffer solution, so that in the same way is not going to affect the pH of our buffer solution pretty much at all. This is important because in Le Chatelier's principle, we know that in our acetic acid that we initially added within our buffer solution, we know this is a reversible reaction. So we create an acetate ion and our hydrogen cation, increasing the concentration of this, our acetic acid, actually, so this goes up, actually shifts the equilibrium closer to the right, farther to the right. So increasing this will increase amounts of this, meaning that more acetate ion is formed that can once again react with our acid, our source of acidity, once more creating acetic acid. So this is very useful in that way. Now let's relate this all back to the Henderson-Hasselbalch equation. So, how does this all come together? Now, this actual equation is given as pH, our dependent variable, what we are trying to find, equals pKa plus log 10 of the concentration of A minus over the concentration of HA. Now, let's dissect this equation and try to figure out what it all means. We know pH, we're very familiar with it. It's just negative log to the base 10 of the concentration of H plus ions. It's what determines acidity or alkalinity. It's just the concentration of H plus ions, because otherwise it would be the concentration of OH ions, in which case we would have POH. POH actually, when added with pH, will equal 14. So that's quite funny because, water, 7. Okay. So what we actually have, we know what pH is. Let's move on to this. We have a log 10, the concentration of A- ions and the concentration of HA ions. Now, log 10 is just a logarithmic way of writing things. It makes really small numbers much or very big numbers quite a lot easier to visualize for us. So we have the concentration of A- and the concentration of HA. We have previously discussed how HA is just our acid within our buffer solution. So this is the acid, actually a weak acid, because that's what is required for it to be counted as a buffer solution. And our concentration of A-. Now we know that A- was our conjugate base, but we didn't actually add any conjugate base within our buffer solution, did we? We added a conjugate salt. Fortunately for us, say we had our sodium salt, we know that in our aqueous solution it completely dissociates, forming our A-, our conjugate base under aqueous solutions in the same molar ratio, so 1 to 1. So in that way we can write our concentration of conjugate base as the concentration of our conjugate salt added. So now we've got this done. So what's pKa? Well, we know P is just a header. It's just whatever comes after it in brackets for our negative log of base 10. So it's negative log base 10 of Ka. Now what's Ka? Ka is the dissociation equilibrium of our HA, our acid that we add. So this varies from acid to acid. The way we use Henderson-Hasselbalch is usually to determine how pH changes with these two concentrations. We usually have pKa given as a pre-existing, predetermined constant. So for acetic acid, our buffer, our pKa is, I think, approximately 4.756, something like that. The way we actually calculate it is by seeing to what extent it dissociates in water. Now, a weaker acid will have a different pKa to a stronger acid. Now, if we just try to calculate Ka is equal to the concentration of A- ions multiplied by the concentration of H plus ions. We know that our acid is HA, over the concentration of HA, because we know that under aqueous solutions an acid will dissociate from HA, will ionize into H plus and A-. So this is just a standard way of calculating any equilibrium point of any reaction. So we just apply this, name it Ka after HA, our acid, add a P on top, now put inside a log, and there we go, pKa. So we've defined all three terms. So how can we actually visualize this? So we have pH, what we're trying to find. We have pKa. Now let's just say this is a constant. So let's just name this K. It doesn't really matter. We can ignore it. What we're actually trying to see is how pH varies with these two concentrations. So let's try to plot this on a graph. Just try to get this down. Let's put pH on our x-axis, and we'll have, concentration of acid going up like this from 0 all the way, and we have concentration of salt. I think a better way of doing this would actually not be concentration, it would be the ratio, because we would otherwise have 0 to 100, so this would be actually a 50-50 ratio. So let's cross these out and put ratio. So we know here our acid is low, and here our acid is high, whereas here our salt is low, and here our salt is high, and this is pH, given from a low value to a high value. So an acid, high in acidity, will have a low pH. Low pH, acid's high here, so this will be down here. Salt will be the opposite of the acid, so when salt is high, pH will be high, which will be around there. So we have pH being low while acid is high. So it would look something like this. the reason it's curving like this, and the reason it's sort of curving like this, and exponentially decreasing and increasing, coming to a stop, is because of the nature of this equation and the way we write it in terms of logs. That's what gives it its curve. So when the acid, there's a high amount of acid, pH is low. When there's a high amount of salt, high ratio of salt, our pH will be high. This is what we use when trying to find out the pH of the Henderson-Hasselbalch, using the Henderson-Hasselbalch equation. So if we had an equal 50-50 ratio of acid to salt, this would actually just be log 10A over A, giving us log 10(1), which we know is 0. So pH would actually just equal pKa. So at this middle point, pH is equal to pKa. And if we know that our acid, our HA, was high up here, and our salt was lower down here, we just extrapolate this curve and we follow it down to this pH level. And that's how we use the Henderson-Hasselbalch equation.